So in this video we'll be seeing how to handle the write request for our IO driver. So let's see the flags in the device object. So we have seen the IO create device function. It will return the pointer to the device object. So in that you can set this flag. So few flags are device object buffered IO. So what this tells is we want to do the buffered IO operation whenever there is a write operation. So in this buffered IO, the buffer will be copied into the device non-paged memory, our driver's non-paged memory. So within this IRQL request, when you go higher in the IRQL request, you will not be accessible to the paged memory. So the contents of this buffer will be copied to our driver's non-paged memory, so we can access like an exclusive manner in the direct IO. So in this direct IO, the buffer will be copied into the system's virtual memory. So the user mode address contains the contents the application wants to send. So in this direct IO, the contents will be copied into the system's virtual memory space. And there is another method, that is directly accessing the user mode address. So we'll be seeing the buffered IO successfully, and the direct IO will not work because we need to use another function, and that function is not there in Rust. So it's a macro in the header file. So let's see the application's code. So this is the code I have written. So what this code does is, so up to here we have opened the file handle to our symbolic link. From here onwards I have created bytes hello there and printing the buffer's address and writing to the symbolic link using the write file function. So this is general common high level Windows API we have seen in the malware development series. And we are also printing the number of bytes written. So what we are going to do is we need to set this flag to the buffered IO or direct IO. If you do not set this flag, by default the address of this buffer will be sent in the IRP request. So here you can see the IRP structure. So the user buffer contains a pointer, so that pointer is nothing but this one, this buffer. So now here after the device has been created, you can say driver.flags, and here the documentation says the higher level drivers are this member with the same value. So and this value is 4. So we can see the direct IO first. So I am going to comment this one. We'll be using this in the later in this video. So up to now it is same we have seen in the previous video. Now we are going to register our dispatch routine for the IRP major write. IRP MJ write and IO. So let's say this as IO write. So this is the function we are going to write. No mangle, don't change the function name. So the parameters are same as the IO create close function. Again we can copy that code getting the IO stack location. So now let's go and continue. So before running our driver, let's put breakpoints, test driver, driver entry, and IO write. That is the function we just created. And we will get the first breakpoint hit. So this is normal driver entry function. We can continue. And let's execute the program. I have already copied this one, and we can see the IO write function breakpoint has been hit. And again, let's inspect the parameters, the device object, and second one is IRP. So the second parameter will be stored in RDX. So here you can see the user buffer contains some pointer, and you can actually copy this and view the contents at this, and you can see the contents hello there. So this should not be private memory to the process. If it is, then our driver cannot access. We should be in the context of the thread or the process the process is actually calling. So otherwise we will get the blue screen of death. And one more thing I wanted to show you is, so in this call we will get the IO stack location for our IRP. Now let's put a breakpoint here. So let's continue. So sorry for previously there was an error and blue screen of death has been happened. I don't know why, but now it seems fine. I did not modify any of the code. Now in the RAX register you should have the pointer to the IO stack. Now you can notice this address B88E16EF0. So let's also first read the contents of IRP. So the IRP has been stored in the RSP press 28 on the stack. So copy this address, and the size is 118 and the last member is 78. So let's go and read the bytes after this 78. So just we are trying to peek after this last member, and you should see the same value, the IO stack location 16EF0, 6EF0. So 6EF0, I think this is this one, FFC5 8B88 8B88 E1 6EF0. So here you can see in the IRP structure only you will have this IO stack locations. So these IO stack count. You can also see the stack count is 1, so there is only one IO stack location, and the address is this one. So you can copy this one and parse this as IO stack location RAX, and you should see the major function 4, that is the write value IRPMJ write, and the parameters. So you will have the contents of the buffer and the length as well. So here this is the entire union. The entire union contains 32 bytes. So you can see 8 and 28, so hexadecimal 20 bytes, so that is 32 bytes. And if the major function is 0, that is create, then you need to parse these 32 bytes into the union of create. So this structure will be parsed over the contents of these 32 bytes. Now our major function is 4, right? So because the 4 has been the IRPMJ write. Now if I go and click on this write, so you will get the information about this length. So the length is C, so hexadecimal C means 12. So you can count the number of bytes here: 1 2 3 4 5 6 7 8 9 10 11 12, including the null bytes. So the count of the bytes will be stored in the length as well, and also other additional information will also be stored in the IRP as well. So in the IO status block, so in the later in this video we will be seeing associated IRP and MDL address. So for now let's concentrate on our IO status. So this is the 16 bytes. So here you need to fill the status or the pointer. So whenever you do something like the function returns a pointer to the variable, then you can write that pointer here. So we have seen the functions like this, allocating some buffer by the function itself, and what we need to do is we need to pass a pointer to the variable. So this function takes the pointer to variable and allocates the buffer and writes the address of that buffer into this variable. So you can do like that. For now we are just putting the status as 0. We did not put anything. We can try to put here, and the information is the number of bytes the operation has been done on. So here the write operation, we can set this to like 5 or 6. Actually we need to set to the length of the contents we have written, that is previously we have seen this length. So you need to put this number of bytes at this here. So after setting the number of bytes, that value will be returned into this write file function. So here you can see we are passing the bytes written. So this information whatever you set here will be stored in this variable. So that's why I am going to print this number of bytes written. Okay, now we are going to complete this IRP. So this is called completing the request. So we need to set this information manually, and then we need to call this IOF complete request macro. So it takes the IRP, and the second one is priority boost. So since we are completing this quickly, we can put IO no increment. The MSDN also specifies the default priority boost for the devices. So we are file device undefined, so IO no increment. Okay, so let's go and do that. Let's complete this IRP request. So from the IRP structure, the IO status is 30 bytes, 30 hexadecimal bytes. IRP plus IO status block. and in the IO status block the first one is pointer, or we can say status, depending upon the operation. And the last second one is information, the number of bytes. So we can go and actually write the contents. So IRP as U size. So we are treating this IRP as an U64 address, and then adding hexadecimal 30. So if you add hexadecimal 30, you will get to this point IO status as constant. You need to read 16 bytes. Yes, you need to read 16 bytes. So at this point what you need to do is, we are going to write the status. We can write status success, the value is 0, and copy the same, paste here. Now we need to add +8 because we are going to now copy the number of bytes we have performed the operation on. So +8 as constant U64. I'm sorry, this is also U64 because we are going to write 8 bytes. So you can see 0, 8, and this information is also 8 bytes. So now I can tell 0xC. So actually you can read the contents of the length here. We have just read. So from the IO stack location, let n bytes is equals to so from here onwards you have the parameters. Offset is 8 plus 0x8. You will get to the parameters, and here this is the entire contents are 32 bytes. In the 32 bytes you can see the length is 8 bytes. So parameters dot write. So you can read 8 bytes. So we have read the 8 bytes. Now you can paste these 8 by n bytes here. So that contains the length of the buffer. Okay, so now you can see the buffer address is this one. So 1A760840, that is the user buffer, and 1A760840. Okay, so you can see this is the correct address, and the number of bytes written is 0 because we did not set anything. Now let's go and see whether it updates the value or not. Okay, sorry, we are mute, so we are doing changes, right? So and now let's run our program, and you can see the bytes written are 12, so I did not put breakpoint. But anyway, you can see the output. So we have copied those xc value, and we have written in the IO status block information member. Now let's go and uncomment this one. So we are trying for direct IO. And let's also complete this request. So after we have written this the information in the IO status block, we can actually do this IO complete request. So the first parameter is pointer to IRP, and second parameter can be 0 for normal boost. So let's continue and let's start. Okay, now we have hit the breakpoint and continue. So let's run the program, and we should hit the breakpoint at the IO right. Okay, now we are using the direct IO. So in this direct IO, so RDX, that is the IRP, and here so I found the error. So this is not driver object, this is device object dot flags. So I always get confused because they both starts with D. So my bad. Let's run this again. Let's compare this. So we got the pointer to the device object. We are referencing that pointer, so we will go to the device object. So device object dot flags. So my bad, it's a huge mistake. previously I thought the driver is not copying properly, or it is loading the old one. Sorry, let's run this program and we will hit the breakpoint. Now let's see the IRP at RDX, and now you can see the user buffer is null, and here in the associated IRP, so I have changed the value to 4 to the buffer IO. Sorry for okay, so mistakenly I thought thought to test this one buffer IO, so I changed this to 4. Okay, let's see the buffer IO. So in this you can see the system buffer, so you can directly copy this one and view the contents at this address. So you can see the hello there, and the length is still can be calculated from the length parameter we have seen from the IO stack location. So let's put a breakpoint at that. So the major function 4 and the parameters we need to check for right. So the length is C. So let's go and read the contents, and let's go and print with the debug print. So in this buffer IO from the IRP we need to get to this 18 offset for the associated IRP. Let's call this as sys buffer. Plus 0x18. So we are going to read 8 bytes at this address, at this offset. So this you can calculate the difference. This is also 8 bytes. So this is a union, and we have this address. So we can go ahead and print the contents. So one more thing you need to be very careful is you need to see whether this string is ending with null byte or not. If this string is not ending with null byte, then you will try to read the other memory and you will get the blue screen of death. So you need to be very careful for the null byte. We are not going to check in our program because we know there is a null byte at this end, because we are the only ones sending the string. Okay, now let's continue, and we should see the 12. Let's also run the debug view. And we can continue this. You can also see the print statement from the IO create close function we have created. And we have got an error. So let's see what we have done wrong. Okay, now we got the contents. I don't know why there is a blue screen of that previously. Okay, now let's see the direct IO. Let's go and copy the value, and we need to comment this one. So now we have hit the breakpoint IO, right? Now in this case, you should see the direct IO. So here you can see the MDL address. So this is our system's virtual address. You can click on this MDL address and you can see the contents. You will have the eProcess pointer, so you can copy this one and eProcess and paste here, and you can find image file name and the tokens.exe. so this is the process our application is calling the write operation. And here you can see the starting virtual address. You can copy this one and add the byte offset. So if you add these two values, you will get the contents of this our buffer. Hello there. So you cannot access this via driver, so we just printed in the Windows debugger. We need to use the function called get system address for MDL safe. So this is the macro that returns non-paged system space virtual address for the buffer that specified the MDL describes. So you will pass the MDL address, so you will read the contents at this offset 8 and pass that value here, and priority normal page priority, and this is included in the WDM header file. For rest there is no access. You need to generate the bindings on your own, so it's going to take some time. So it's just like what we have created here. So we have written our own bindings here, right? So what we are going to do is we are going to use the bind gen create to create the bindings for this macro. So I will try to create the binding for this function in the future. If I create the binding, then we can use this to copy the contents. So for now we are not doing any coding to print these contents. So that's all for this video. We have seen how to handle the write operation for our driver. So there are so many errors in the video, but sorry, my bad. The major error is being writing for the driver object flags. So instead we should write to the device object. So these two are confusing words, device object and driver object. So anyway, so that's all for this video, handling the write operation with our driver.